Hi, this problem is about a point particle P that is connected with a string with a fixed point O on top of a table, like this, okay, so that the string can hang over the edge of the table like that, okay. In this screen you can read the statement of the problem in detail, so please pause your video and read it carefully. Okay, and the problem asks a number of questions that you can read here. So one of the key aspects of this problem, as pointed out in the hint at the end of the statement, is about the geometry of the string hanging on the edge of the table. So since the string can slide left and right over the edge of the table without any friction, that means that this angle here, okay, the angle that this segment of the string makes with the edge of the table, and this angle there, which is the angle between this other segment of the string and the edge of the table, are equal to each other. So let us begin with the preliminaries of the problem. One of the first aspects that we have to look at in every problem is the number of effective degrees of freedom in the system that we are studying. In this case, the system is this particle connected with the constraint of the string to point O. So a free particle, in general, would have 3 degrees of freedom if it was moving freely in space. In this case, the constraint, due to the string connected with O, removes 1 degree of freedom, and therefore we expect this problem to have 2 effective degrees of freedom. In fact, those degrees of freedom are represented here by variables theta and phi. Okay? It is important to understand what these angles mean. So the first angle, theta, is the easier to understand, represents the orientation of this segment of the string with the x0 axis. Okay? When the angle theta increases, the whole device, okay, the string and the particle, will move to the right, and when it decreases, they will move to the left. That represents one of the degrees of freedom of the particle. The other important degree of freedom is the angle phi. Okay? Angle phi is related with the separation of the particle with respect to the vertical, okay, the vertical plane that passes by the edge of the table. All right? So if you think of the plane created by this segment of the string, okay, and the edge of the table, that two lines define a plane. That plane is separated from the vertical plane by an angle phi. So angle phi represents the motion of the particle in and out under the table. All right? So in total, there are 2 degrees of freedom in the system. So the next thing that we want to do before we answer any other question is to define some auxiliary vectors that can help us obtain the solution of the problem. So as you can see in this drawing, I have replicated the drawing that we have in the statement of the problem. Okay, so here is basically the reference frame that we start with. Here, this is the string, which goes from O to Q and then all the way to point P. Okay, this is the edge of the table, and we have the angles theta and angle phi. Okay. So the first thing that we are going to do is to replicate our vector basis, draw it on top of point Q. Okay? The reason to do that is nothing special, it's just a small trick to help us visualize better the rotations that we are going to do next. Okay? So this is the direction of J0, and this is the direction of I0. Okay. So the first vectors that I want to define, if you remember, I mentioned before that this segment of the string from Q to P and this edge of the table, they are 2 lines that define a plane that differs from the vertical plane that passes by the edge of the table. Okay? So in order to visualize better that plane, let me draw these lines. Okay? So this is a vertical line, and this is a line that is also an angle phi from the vertical. Okay? And the plane that I'm referring to is this plane. Okay? It is a plane that contains the segment QP, okay, and the edge of the table. So we are going to define some new vectors. Okay? One of them is going to be this one, okay, which I'm going to call I1. I1, there you go, okay, and the other one is a perpendicular vector that goes like that, okay, this is going to be K1, and for completeness I'm also going to call the direction of J0, I'm going to call it J1, so we have a full vector basis, okay. The advantage of these new vectors is that I1 and J1 define the plane where this segment of the string is, okay. As always, whenever we define some new vector basis, it is necessary to write down the vectors that we have just defined graphically. Okay, we also want to do that mathematically. So, in the case of I1, okay, as you can see, when phi is small, it's basically pointing downwards. Okay, so the cosine of this vector, when we project it in the old vector basis, okay, we get the cosine in the minus k0 direction, all right, and the sine in the I0 direction. Therefore, we will write here sine phi I0 minus cosine phi k0. Okay, that is the definition of I1. In the case of J1, as we said, it is basically J0, so nothing special there. And in the case of K1, okay, perhaps the drawing I made here is not the clearest one, but the angle phi appears here as well. Okay, this is phi. Okay, it's the angle between I0 and K1. Therefore, we have the cosine of phi falling along I0, okay, and the sine of phi going along K0. Like that. Okay, so that is the first vector basis, auxiliary vector basis that we have defined. Next, I want to do another rotation so that I get an axis oriented along the segment QP. Okay, so that rotation is going to occur about the axis K1. Okay, I'm going to rotate about K1, the red vector basis, and I'm going to orient the new vector basis like so. So this is going to be the direction. This is going to be the direction I2, okay, perpendicular to that, but always in this plane, we will have J2, all right, and then this K1 will coincide with K2, okay. So perhaps the most relevant angle that we have here, which we need to compute, is this angle, okay, the angle between J1 and I2, which, as we said from the statement of the problem, it is the same as this other angle that appears here, all right? So I think it's time to compute what is the value of this angle. In order to do that, we are going to do an auxiliary drawing, okay, looking at the picture from above, from the direction of K0. So when we do that, we see the table as a rectangle, all right, like so. And the vectors I0 and J0 look like that. Okay, this is point O. Point Q is somewhere over here. Okay. From this drawing, we see perfectly well what is the angle theta, okay, over here. That's what I have represented here. And using this triangle, it's very easy to compute the value of this other angle here, which is the one we are looking for, okay, because this is equal to this, okay. So as you know, the angles of a triangle have to add up to 180 degrees. So this is a straight right angle here, okay. So this is 90 degrees. Then this means that theta plus this other angle have to be equal to 90 degrees, okay, which is the same as pi half radians. Therefore, this angle, let's call it beta, okay, to give it a name. We have that beta is equal to pi half minus theta, okay. So that's the angle that we have right here. This is the angle beta, and this is also beta, okay. There you go. So now we are in condition to write down the expressions for the vectors of basis number 2, okay, in terms of the angle theta. So if you look at the plane, okay, the plane over here, which is composed by the segment QP and the edge of the table, if this is beta, okay, as we have seen, beta plus theta is equal to 90 degrees by half. That means that the angle that appears here is theta, okay? So let me move this away. Okay, so this is phi and this is theta, okay? So knowing that this is theta, it's relatively straightforward to write down the vectors of basis basis 2 in terms of basis 1, okay? So you can see the vector I2 gets the cosine projection along I1 and the sine projection along J1, okay? So we have cosine theta I1 plus sine theta J1. Then for the vector J2, okay, the angle theta appears here as well. Okay, this is also theta. So we have the cosine along J1, okay, and minus sine in the direction of I1. So minus sine theta I1 plus cosine theta J1. And finally, K2 is the same as K1. Okay, so these auxiliary vector bases are going to be very useful to compute the solution of the problem. So now we are in conditions of answering question number 2 of the problem. Okay, we are asked to provide a vector that goes in the direction of Q to P. All right, so we have already that. The vector that goes from Q to P is I2. All right, so we just have to provide the vector I2, okay, which we have over here, in terms of basis 1. We can leave it like that, okay, so that would be a correct and valid answer, since we have already defined what are the vectors I1 and J1 over here. Or if we want, we can also write this in basis 0 by replacing I1 and J1 with these expressions, okay? So when we do that, we obtain this result, okay, cosine theta sine phi I0 after replacing this over here. Then I'm trying to write everything in order, so the next term is going to be this one, okay, J1 is J0, so that gives me that. And then in the K direction I have this part times this, okay, so we get a minus cosine theta cosine phi in the K0 direction, okay? So that would be our answer to the second question in the problem. So we are now in conditions to start solving the kinematics of the problem, okay? So that basically corresponds to question 3 in the statement. Now, the first thing that we want to do is to find out the position, velocity, and acceleration of point Q, okay, which is the point where the string touches the edge of the table. So that is relatively easy to do if we, again, work out with this triangle here, okay? So as the statement of the problem says, the distance between O and the edge of the table is D, okay? That's the distance that we have from O to this point over here without name. Now, using some trigonometry is relatively easy to find out that this length of the string, okay, is going to be d over the cosine of theta, okay? And this other edge of the triangle is going to be d times the tangent of theta, all right? So once we have that, and using all the vectors that we have, finding out the position of point Q as seen from reference frame 0, okay, from the origin, is relatively straightforward. So that position is given by moving from O to the edge of the table, okay, a distance d, that gives us d times I0, all right, and then moving to the right along J0, a distance d tangent theta. So there you go. that gives us the position of point Q. Now, once we have the position of a point, obtaining the velocity and acceleration is as simple as taking derivatives there. So the velocity is going to be the derivative of this in time, okay? Since we are taking derivatives in reference frame 0, the vectors of basis 0 are constant. So the first term doesn't yield any derivative. For the second one, we have the derivative of the tangent, which we can write as 1 over the cosine square of the angle, okay, times the derivative of the angle, of course, in the direction of J0. Okay? So that gives us the velocity. For the acceleration, we just need to take another step of derivation. Okay, so let's do that. So when looking at the velocity, we have to take derivatives of this term times this term. Okay, so we have, on the one hand, d sine theta cosine cube of theta, okay, theta dot with the other theta dot that gives us theta dot square, okay, then plus d cosine theta square theta second, okay, so all this in the direction of J0. So that is the kinematics of point Q. Now, for the kinematics of point P, okay, one thing we can do is to break down the vector RP0, okay, that is the vector that goes from O to P, which is a complicated vector. We can write that as the sum of two vectors. One vector that we already have, which is the vector OQ, that is the position vector of Q, okay, okay, plus the vector QP, all right? So there you go. That is the way that we are going to compute this position vector. So this one, we already have it here. Let's just write it down. So it's this vector. Okay. And the question is, how much is this? All right. So we know the length of this segment. Okay. So the total length of the string is, as the statement of the problem says, is L, all right? So we know that some part of the string is in the segment OQ. That part of the string is d over cosine theta, okay? So the rest of the string has to be L minus d over cosine theta, okay? So that is the magnitude of the vector that goes from Q to P. Now we need to provide the direction to this vector, okay? And we already have it, is the vector I2. So we just write here I2, okay? This expression is valid and it is correct because we are using vectors that we have already defined, all right? But it is a little bit cumbersome because it is mixing vectors from different bases. Okay, so that's all right, but if you want, you can try to reduce everything to a single vector basis to make it more compact. So that's what I'm going to do here. I'm going to bring this vector all the way to basis 0, so we can get an expression that is only in basis 0. Of course, I could do the reverse. I could bring these two vectors to basis 2 and work in basis 2. Although, if I do that, I have to be careful that when I take derivatives in reference frame 0, the vectors of basis 2 are not constant. Okay, so I would need to apply the Coriolis theorem to compute the vector derivatives correctly. Okay, so the first part of the expression remains unchanged because it is already in basis 0. I just have to transform vector I2. I already have the correct expression here, so I just need to plug this in place of I2. So when I do that, in the direction of I0, I get d, which I have from here, plus this term, okay? So L minus d over cosine theta sine phi, okay? All that goes in the direction of I0. In the direction of J0, I have this guy and this part multiplied by sine theta. So that gives me plus d tangent of theta plus L minus d cosine theta sine theta. All right. All this goes in the direction of k0. And then finally, I have in the direction of k0 this times this. So that gives me a minus L minus d cosine theta cosine phi. Okay, so this is what goes in the direction of k0. So there you go. That is the position expressed in basis k0. Before we go on, it is desirable to simplify this expression a little bit, since we are going to need to take derivatives there. Okay, so in particular, we are going to multiply through the cosine here, and here by the sine, and so on. And as you will see, this expression can be simplified somewhat. So for the first term, we would have this, all right, times the sine of phi. This is what goes in direction I0. For the second one, look, we have here d over cosine times sine. This is going to be the tangent with a minus, so this cancels out with this term. So we basically end up with L sine theta k0, okay? And then in the last term, we have L cosine theta minus d cosine phi k0. Okay, so there you go. Now, for the velocity, we need to take derivatives here. Okay, so let's do that. Looking at the first term, the derivatives that we have are minus L cosine theta dot, okay, when we take derivatives of these parentheses, times sine phi. Then we have the parentheses times the derivative of the sine. So that gives us the cosine of phi dot. Okay, this is all that we have in the direction of I0. For the second term, we just have L cosine theta dot k0. And for the last one, we have the derivative of the parentheses. So as before, this is going to be minus, with a minus becomes a plus, L sine theta dot, okay, times cosine phi, okay, plus another term, which is the parenthesis itself, okay, times the derivative of the cosine. So the derivative of the cosine is the minus sign, with the minus becomes a plus, which I already have here, okay, so that gives me sine phi dot, and all this goes in the direction of k0. All right, so that is your velocity, except that here this is a sine. Okay, sorry about that. So this is a sine. Okay, so lastly, we have to take another step of derivation for the acceleration. Okay, as you can see, every step of derivation we are increasing the complexity of the expressions, so it is advisable to simplify the expressions whenever possible. We would have obtained probably simpler expressions if we were working in the vector basis too, okay? But as always, there are advantages and disadvantages with every approach that we take. So starting with the I0 term, when we derivate, we obtain the minus L cosine theta dot square sine phi minus L sine theta second sine phi minus L sine theta cosine theta, theta dot, I mean, cosine phi dot, okay? All these terms come from just this one, okay? So we now have to deal with this other one over here. So bear with me, we have to add L sine theta dot with a minus, okay, so that goes like that, times cosine phi dot. Then we have minus L cosine theta minus d sine phi dot square, and finally we have a plus L cosine theta minus d cosine phi second. Okay, so all this is what goes in the direction of I0. All this. Okay. Next comes the J0 term. This is the nice one because it's a little bit smaller. So we have a minus L sine theta dot square plus L cosine theta second. Okay, so there you go. That is what we have in the direction of J0. And then finally we have to deal with the last one. Okay, so we have L cosine theta dot square cosine phi plus L sine theta second cosine phi minus L sine theta dot sine phi dot. All right, so that is what comes out of this guy. And then we have to deal with this one. So we get a minus L sine theta dot for this parenthesis times sine phi dot. Okay, then if we continue we get plus L cosine theta minus d cosine phi dot square. And finally we get plus L cosine theta minus d sine phi second. Okay, and all this is what goes in the direction of K0. Okay, so there you go, the expression for the acceleration. So as this expression is a little bit long and it can be simplified somewhat, okay, and since we are going to use it in the equations of motion, I have rewritten it over here, okay, by grouping together some of the terms. All right, so it is not much shorter, but it gains some compacity. So here goes the term in the I0 direction, the J0 direction, and the K0 direction. So we are ready to move on into the dynamics of the problem. Okay. So first of all, in order to answer question number 4, we want to find out what are the forces acting on point P. Okay. So we are working on an inertial reference frame, S0. So there are no inertial forces. The only forces acting on P are the weight. Okay. P is a heavy particle, and here is the vector of gravity. So we have a force. The weight pointing downwards, all right, and we also have the tension force of the string. Okay, so the tension force is a vector that points in that direction. So in order to write mathematically these two forces, okay, we are going to use the vectors that we have already defined. So on the one hand, we have the weight force, which is equal to the mass of the particle P and the gravity vector, okay? And the gravity vector is basically pointing in the minus K0 direction, so we may as well write this as minus mg K0, okay? Then for the tension force, since the tension goes in the direction from P to Q, the direction of that tension is the minus E2 vector, okay? Minus I2 vector. So we don't know the magnitude of this force yet because it's a constrained force, it's a reaction force. So we have to introduce a new unknown of the problem, which is a parameter t, okay? So we can write this vector force as t in the direction of minus I2, okay? So there you go, those are the two forces and the only forces acting on P. So the next step is to write down the equations of motion, okay? And as the problem statement says, we want to obtain a couple of second order differential equations for theta and phi respectively, okay, free of any other unknowns, all right? So let's see how we can do that. So first of all, we have here our acceleration, okay, that we obtained in a previous step. And here we have the forces. So if we call these terms by names, okay, so we avoid writing them. So let's call this term, all this, let's call that AX0, okay, the acceleration of point P in the direction x0, okay. Let's call this term AY0, and this last term, let's call that APC0, all right? Then the equations of motion for particle P are relatively simple. So we have on the one hand M APX0, okay? That has to be equal to all the forces acting on the I0 direction, which we will compute in a moment. Then we have the acceleration in the I0 direction and the acceleration in the C0 direction, okay? So in order to have the forces in this basis, okay, this is in the direction of I0, okay, this is in the direction of J0, and this is in the direction of K0. So in order to have the forces in this direction, we need to project the forces in this basis. So we see that the weight is already in the K0 direction, so that's fine. But the tension is in the I2 direction. So we need to go back to our definition of I2, okay, which we have over here, all right, and rewrite the tension in terms of that expression. So we have a minus T cosine theta sine phi in the I0 direction, okay. Then we have minus T sine theta in the J0 direction, and finally we have a plus T cosine theta cosine phi in the K0 direction, okay. So now yes, we can take these expressions and place them over here as corresponds. So for the weight, we see that we just have the K0 direction as we said, so we have here a minus G, mg. Then from the tension we have this component, okay. For the other two equations, we just have tension components, so we have here a minus T cosine theta sine phi, okay, that's the component in the IC direction. And then for the J0 we have a minus T sine theta, okay. So these three equations are the equations of motion of the particle, but as you can see, they involve an extra unknown, okay. So the left hand side is the mass times the acceleration. In that expression, in those expressions, only things that depend on phi and theta and their derivatives exist, okay? But on the right-hand side, you see that we have introduced this new unknown, which is the tension, and it appears in all three equations, all right? So the question is, can we get rid of this tension parameter, okay, this tension variable, in two equations at least? How can we do that, okay? So there are basically two ways to do this, which are essentially the same, okay? So we can do as we have done here and write down the three equations of motion in, for example, basis 0, okay, which involve the tension, and then find out linear combinations, two linear combinations of these three equations where we can eliminate the variable t, okay? So that's possible to do. The other possibility would have been if instead of computing the acceleration, okay, and instead of doing the kinematics of point particle P in basis 0, if we have done all that work in another basis, okay? A basis where at least two vectors, okay, actually two vectors, were perpendicular to the tension force. And that would have been possible, okay? As you can see, we already have a basis where one vector, I2, is in the direction, actually in the negative direction of the tension, okay? And two other vectors, that would be J2 and K2, are perpendicular to this segment, okay? So if we had expressed our acceleration in that basis, and if we have projected our forces in that basis, we would have already obtained one equation that depends on the tension, all right, but two other equations that are free of the tension, okay, which is the expressions that we are looking for. So on top of obtaining probably expressions for the acceleration that are simpler in basis number 2, we would have already obtained the expressions that we wanted in this part of the exercise. We would have obtained the two equations of motion that are independent of the tension, all right? So, as I said, this is one of the things that we learn with practice. Sometimes we pick a particular vector basis where we have to work a little bit more, and there is always an optimal choice where we have to work less, okay? In this particular problem, it would have been probably preferable to work in basis number 2, because we would have already obtained these expressions for the equations of motion that are independent of t, okay? But it is not a problem. We can do all the exercise in basis 0 as we have done, okay? And now we can find the linear combination that we want. So once we have these equations, okay, what we can do is, as I said, we can multiply them by something and then add them together. What we want is that those linear combinations are such that the tension doesn't appear, okay? So one possibility is to multiply the first one times the cosine of phi and the last one times the sine of phi, okay? When we do that and we add together the two expressions, you can see that the term that depends on the tension is going to disappear, okay? That's going to cancel out. So that's one first linear combination that yields an equation that does not depend on t, okay? The second one is a little bit more complicated, but you can check that this makes sense, okay? We can multiply the first one times minus sine of theta sine phi, okay? The second one by the cosine of theta, and the last one by the sine of theta cosine of phi, all right? So when you add them together, the term of the tension is going to disappear, okay? And those expressions, after you do that multiplication, and when you, of course, you have to multiply on the left-hand side and on the right-hand side, the result is going to look like this. So I'm already going to divide by the mass on the process, okay? So on the first case, I'm going to get this expression, okay? So I'm going to get minus 2L theta dot phi dot, okay, on the left-hand side, sine theta. As you will see, a lot of terms are going to vanish after multiplying by these vectors, okay? So that will be the first term. Then I get this other term, okay? And all that, after dividing by the mass, is equal to minus g sine theta, okay? Sine phi, which comes from multiplying here. That's what yields this term. So that is the first equation that I obtain, okay? As you can see, the left-hand side is also very simple, okay? So when I multiply this by the cosine of phi and this by the sine of phi, okay, and I add that together, many of the terms cancel out, okay, as you can check if you do this exercise, all right? And all that remains is this, okay? So that is my first equation that does not depend on t. For the second one, okay, I multiply by these expressions here, okay? So I have to do that also on the acceleration, and also a lot of terms vanish, okay? So the only thing that remains is this, L theta second plus L cosine theta minus d, okay, times phi dot square times sine theta, okay? So that's what remains. And on the right-hand side, what we have is minus g sine theta cosine phi, okay? So these are the two equations that the statement of the problem asks us to find. Okay, so I will say it again. What we have done here is a little bit more cumbersome. Okay, we have worked in basis 0, so we have obtained pretty long expressions for the acceleration of the point particle p, okay, in this basis. And after writing down the equations of motion in this basis, we needed to find linear combinations, two linear combinations, okay, multiplying by these factors and adding together, that yield expressions that don't depend on t. Okay, this is completely equivalent to working directly on basis 2. Okay, so if we had done that, the expressions for the acceleration would be simpler. Okay, and actually they would correspond with these expressions for the directions of k2 and j2, right? And this is what we would have obtained directly when we wrote the equations of motion. So we didn't have to find any linear combinations in that case because we already have two expressions that don't depend on t. So for the last part of this problem, we have to answer some specific questions. The first one relates with the work that the tension force exerts on P, okay, whether it does any work or not. And the second one, the last one, is about the energy equation. Okay, so both of them are related. So starting with question number 6, what we want to check is whether the tension force exerts any work, okay, on P, and that is equivalent to finding whether the dot product of the tension times the velocity of the particle is at all times equal to 0. Okay, if that expression holds for all times, then the tension does not exert any work. Okay, so I have copied over the expressions that we already had for the tension force. Okay, remember that it was minus ti2, okay, which translated into basis 0, it is this vector, okay, and the velocity of particle p in that basis. All right, so what we have to do is to compute the dot product of these expressions, these two vectors. All right, so let's start by computing the dot product of the first part. Okay, so I'm going to write it here like this. Okay, so when I multiply this expression times this expression, okay, what I will get, let's see if we can do it sufficiently compact, is sine theta cosine theta sine phi square, okay, times theta dot, okay, that comes from the first term, plus L cosine theta minus D, then cosine theta sine phi cosine phi dot, okay, and all this is multiplied by t. Okay, so let's put the t over here, like so. Okay, so this is the first part of the dot product. We have multiplied this times this. Okay, so next comes the j part. Okay, so we have, and by the way, let me check that I didn't do any mistakes. Here we had a minus and here we had a minus, so this has to go with a plus. Okay, sorry about that. And here we had a minus and here we had a plus, so this has to go with a minus. Okay, it's always important to check that we are putting the signs correctly. The next one has a minus t L cosine theta sine theta theta dot. Okay, that's all that we have from this times this. Okay, and finally we have the third part. Okay, so we put it over here. So we have on the one hand t L sine theta cosine theta, okay, and then cosine square of phi theta dot, okay, and then we have a plus t L cosine theta minus D, okay, times cosine theta cosine phi sine phi dot. Okay, so that's all there is to the dot product. So we have to check whether this expression is identically 0 for all times or not. Okay. All right, so let's check. We can see that, let me mark with a different color. We can see here that this term, for instance, and this term, they look very similar, except that this one goes with the sine square and this one goes with the cosine square. Okay, so we can add the two of them together into a simpler expression, which looks just like TL sine theta cosine theta. Okay, and theta dot. All right. So that's one of the parts that we have. We also see that these terms are basically the same thing. Okay, they are actually the same thing. All right. So they are going to cancel out. This will go out with this. Okay, so there is nothing else that we need to worry about there. And the last one, this one, well, we just copy it over here, and we immediately see that the two terms that we have in the dot product are identical and with opposite signs. So this is identically 0. Okay, this means that the tension force is never exerting any work on the particle in this problem. Okay. Again, if we have worked in basis number 2 directly, it would have been very simple to check that the velocity of P doesn't have any component in the direction of I2, which is the direction of the tension. All right. So computing this dot product would have been simpler in that basis. For the last part of the problem, the last question, we need to check whether the mechanical energy is conserved or not. Okay, and we have already done all the work here. So important for the energy conservation is to check whether the forces that exert work are conservative or not. In this problem, we have just checked that the tension is not exerting any work, so we don't need to analyze this force. Okay, it's not going to take part into the energy equation. The only other force is the weight, okay, and as we know, the force of gravity is a conservative force. So yes, the question whether the energy is conserved or not, the answer is yes, it's going to be conserved, the mechanical energy of P. Okay, so to start with that, what we want to do is to compute the kinetic energy and the potential energy of the particle. Okay, so I have started here with the expressions that we already have for the velocity. Okay, so if we want to compute the kinetic energy of the particle P in reference frame 0, okay, we have to compute 1/2 of mvp0 square. In other words, we need to compute the dot product of this velocity with itself. Okay, so let's do that. We are going to have the 1/2 of m as a common factor for all the expression. All right, and we need to compute the square of this parenthesis. All right. So when we do that for the first parenthesis here, we obtain L square sine theta square sine phi square theta dot square when we multiply this times itself. Then we have 2 times this, so that gives us minus L sine theta sine phi theta dot. It's a little bit long. L cosine theta minus d. Then cosine phi dot. Okay, and then finally we have the this square. So we have the L cosine theta minus d square cosine square phi dot square. Okay, so that's the first part. Let's put here a bigger parenthesis as we are going to add here the next term. So the next term is this square, so that's the easy part. We have cosine of theta square, theta dot square, and that's it. Okay, and the next one is this square. So again, we have to deal with the square of this parenthesis. So we have L square sine square cosine square theta dot square. Okay, after squaring this, then we have the 2 times L cosine theta minus d sine phi dot times this. Okay, So we have sine theta cosine phi, and then theta dot, okay? And then finally, this parenthesis square, so L cosine theta minus D square sine square phi dot square, okay? And this is all there is to it. And of course, here a lot of terms are going to simplify, okay? So for example, here we have the same thing, okay, except that we see that this is with the sine square and the cosine square of phi, all right? So when we add the two together, we are going to get something far simpler, okay? So let us put here the common factor 1/2 of m again. So this with this is going to give me L square sine theta square theta dot square, okay, after adding the two together, okay? But as you can see, I also have this one here, okay? So that gives me the cosine square of theta. So in the end, all these three terms become L square theta dot square, okay? So that's a big simplification right there. Let's see what else can we simplify. So if we look here, we see that we have this term and this term, okay? So they look very similar, they have the same parenthesis square, but this one comes with a cosine and this with a sine square, okay? So when we add the two together, the cosine square plus the sine square become 1, and we just have the parenthesis, okay, like so, and the phi dot square, okay? And finally, we have to look into this. So let's check. Hopefully something vanishes, or all of it vanishes. So we have this parenthesis is here and here, all right. Then we have the sine of theta, the sine of theta, the sine of phi, we have an L, and we have the cosine of phi, okay? And then we have theta dot, phi dot, phi dot. So the two terms are identical, except that this one has a minus, okay? So when we add the two together, they are going to vanish. So they don't give anything for the final result. So this is all there is for the kinetic energy of the point particle, okay? The next thing that we want to do is to compute the potential energy. So the potential energy due to gravity, okay, of point particle P in reference frame 0 is related to the height of the particle with respect to some datum. For example, we can take the table as our reference, okay? So we need to check what is the position of our particle in the reference frame. So we have it right here. This is the height of the particle with respect to the ground, okay? So we can write down our potential due to gravity as this, okay? So G L cosine theta minus D, okay? Cosine phi, and yeah, we have the minus here, okay? So that's the potential energy. So the equation of mechanical energy states that the mechanical energy of point particle P in reference frame 0, which is the sum of kinetic plus potential energy, okay, as all the conditions are satisfied, is constant in time. All right. The value of this constant we can evaluate if we know the initial conditions. Okay, so the statement of the problem says that initially at time t0, the angles are exactly pi over 3 radians, okay, and the modulus of the velocity is this much, okay, where g is the magnitude of the acceleration due to gravity. All right, so we just have to input those values into our expressions, our general expressions for t and v, in order to find out what is the value of this constant. So the way to do this is to realize that the mechanical energy, okay, the sum of the kinetic and the potential energy in the initial time can be computed with this data, as I said. Okay, so when the velocity, if we choose this expression, if we evaluate this expression at time 0, where we know that the velocity is square root of Lg, okay, we get that the kinetic energy at time equals 0 is just 1/2 of m, and the square of this, so the square root disappears, Lg. Okay, so that's our initial value for the kinetic energy. Regarding the potential energy, we have to use this formula. We don't have another one. Okay, so we have to realize that the cosine of pi thirds, okay, pi over 3, which is 60 degrees, is 1/2. Okay, so this cosine and this cosine reduce to 1/2, both of them. Okay, so at time t0, the potential energy is just minus mg L/2 minus d 1/2. Okay, so when we add together these two expressions, okay, we see that we have 1/2 of mgl, okay, and here we have 1/4 of mgl, okay. So the constant of the kinetic energy is equal to 1/4, okay, because we have 1/2 minus 1/4, 1/4 of mgl, okay, and then we have plus mgd/2. Okay, so that's the value of our constant. So with this, we complete the problem. Okay, I hope that you have learned something useful out of it. Okay, in particular, the importance of choosing the right vector basis to work less. Okay, we have chosen in this problem on purpose the basis number 0, hoping that in the derivation of the velocity we didn't have to apply any Coriolis theorem, but as a result the expressions in that basis are a little bit long, okay, and then we need to do some projections and work a little bit more. So sometimes it's better to choose a vector basis where we know that we need to apply Coriolis theorem when we take derivatives, okay, but which yields smaller expressions. It's always a trade-off of how much work we have to do and the complexity of those calculations. All right, so thank you very much, and remember that you can leave your comments in the quiz, in the survey, in the comment of this video, to let us know how you like this video and if it was useful for you. Thank you very much.